Now I'd like to dig a little bit more into the frequency response, which we'll see more of when we talk about Fourier transforms. But in particular, I want to visualize how the frequency response relates to the Laplace transform of the system. So we'd like to be able to understand this relationship between the frequency response and the Laplace transform, and then kind of visualize how the effect of poles and zeros have on the frequency response. So remember, this frequency response, this h of j omega, is just the Laplace transform evaluated at s equals j omega. So that's why we call it h of j omega, because to emphasize this connection with the Laplace transform. And the definition is this formula right here, h of t e to the minus j omega t. So how should we think about this function? Well, it's a complex valued function on the s-plane, so it's 2D but complex, so that's a little bit hard to think about and hard to visualize. But maybe we can focus just on the magnitude, because that's kind of a bit easier to understand. And so now we can think of this as like a 2D surface, right? So we have the s-plane, and then we have a surface on top of that. So this is like a 3D plot. And you can think of this s-plane as like a rubber sheet, right? And so poles pull up. It's like you stick a tent pole in up below the rubber sheet to kind of pull things up to kind of an infinite peak. That's where the poles do. And the zeros pin the sheet down to 0. So you kind of get this tension between the poles and the zeros. The poles are pulling up, the zeros are pinning it down, and then from that you get to see, if you look along the imaginary axis of the Laplace transform, you'll see the frequency response. So let's try and take a look at some examples to give a sense of what I mean by that. So let's take this transfer function here. We have a 0 at plus 1/2. So here it is right here. Here's the 0 at 1/2. And then over here, if you squint at this a little bit, this is going to be a little bit more complicated. This is going to have 2 complex roots, so two complex poles. And if you wanted to do it, you can do the quadratic formula. So you get minus 10 plus minus square root of 100 minus 4 times 32 is 128. Right, so over 2, so we get minus 5 plus minus, so there we go, minus 5 over here, plus minus 2 square root 7, or square root 7, I think. And square root of 7 is somewhere between 2 and 3, so you can see like somewhere between 2 and 3 here we have this pole. So we have our 2 poles over here. Right, and so now we're looking kind of face down on the s-plane. And so now imagine there was a rubber sheet, and imagine that you stick your finger down and you pin this 0 here, you pin this down to the floor, and then you put 2 kind of infinitely tall spikes on the rubber sheet at the two pole locations. And then what you should get is a kind of surface plot, and let's see what that surface plot looks like. So here's the surface. So here I'm now, remember, so this is the real axis here, so this is the real part of S, and this is the imaginary part of S over here, so real axis and imaginary axis. So now we're going to slice along the imaginary axis, and so what does that look like? So I'm trying to look at where it is so this is the imaginary, so this is the actually s equals j omega. This is where that line is. It's where the real axis is equal to 0. So you can see here we have the 2 poles and the 0 pinning it down over here. And you can see now what I mean by this rubber sheet idea. So we've stuck these 2 poles in there and we've pinned this 0 down. And then you can see you're going to get this little dip in the frequency response, and then it comes back up. And when we plot the frequency, we're plotting it from 0 up, so we're kind of looking at this. So we this top part here. So if we look at this, it should sort of start from something low and then kind of pull upward to be something slightly flatter. So the question is, okay, now if we use our MATLAB to plot the frequency response, what do we get? Well, we get exactly what I said there. We have something that starts out low. It starts out low in that little divot in the rubber sheet there, and then it increases. It increases up to some point, and then it kind of decays back down, right? And so that increase here, this is due to the poles, right? And where are the poles? They're at like they're remember they're kind of set off from the imaginary axis and at 2 points. So if you looked at this at two conjugate pairs, so if you looked at this, if you wanted to plot it in the other direction, you would get also a similar kind of thing. It goes up and it'll come back down. So we get a mirror image if we looked at negative frequencies. But as we'll see, in negative frequencies, if you think about it, a cosine is made up of a positive frequency and a negative frequency. If you think about e to the j omega plus e to the minus j omega, so you have cosine is equal to 1/2 e to the j omega t. So that's at a frequency omega. Sorry, this is cosine omega t plus 1/2 e to the minus j omega t. So we can think of that as something happening at minus omega. The cosine, when it goes through an LTI system, gets affected by, remember, h of e to the j omega. H of j omega. And this omega encapsulates both the plus omega here and the minus omega here. Okay, so this is what happens to our system looking at this rubber sheet. Maybe it's helpful to look at another example, and this time we can make a connection to how these things are implemented. So this is a third order Butterworth filter. What does third order means? Third order means 3 poles. And it's implemented in the following circuit with 2 inductors, a capacitor, and 1 resistor. And if we write out the transfer function of this circuit, as you would, for example, in your circuits class, you would get the following transfer function. You get sort of R4 over S cubed, S squared, and S, and then we have this constant term, the resistance as a constant over here. And this is using the impedance method. We can come up with this transfer function. So now we can plug in some values to get a Laplace transform that is, we don't have all these symbols lying around. We can sort of just pick some numbers. And suppose we make a 4/3 farad capacitor, a 1 ohm resistor, 3/2 Henry, and 1/2 Henry inductors. Now, of course, you'd say 4/3 farads. That's a gigantic capacitor. Or you can have these things called like supercapacitors, which are a little bit smaller, but still like, maybe take up an inch or so, or a diameter kind of on the as a circuit component. So these maybe aren't the most realistic values to use, but they're nice values to use at least to get the math right. So if you were actually working with this in a real system, you'd have whatever your actual components are, and actually part of the trick of designing these filters is to be able to use the actual values of capacitors and inductors and resistors that you can actually find. So there's a constraint on your design in that, can you build it with the components that you have. So the transfer function, if you plug all those numbers in, is very simple. We have this 1 ohm resistor, so we just get this 1 on the top, and then we get a 1 on the bottom, and we get 2s plus 2s squared plus s cubed. All right, so you can use in MATLAB, you can use the command roots. If you do roots of 1, 2, 2, 1 with commas, you'll get out the real and imaginary poles here. Or you can just draw the pole zero diagram, and you'll see that you get 2 poles at there's a pole at -1, and you can see that actually just by plugging in. When you have -1, this 2 will cancel with this 2, and this 1 will cancel with this 1. And then you have poles at -1/2 plus minus something, which you can extract out after you factor out a s plus 1 in the denominator. So we can have three. So this Butterworth filter has, remember, it's third order. So third order means three poles. And here are the poles. They're kind of arranged, if you think about it, you can sort of see they're kind of arranged in like a sort of semicircle of sorts. And we'll see that when we look at Butterworth filters, other examples of Butterworth filters, we can see a little bit better how they decide how cleverly the poles are positioned in order to get the effect that you would want. Okay, so then the question is, what is the surface that looks like that you get out of this Butterworth filter? Now here, it's going to be, so there's only the poles pulling up the sheet, and we have no zeros pinning it down. So we're going to get sort of some tent poles in there, and in particular we have this conjugate pair, and we have something in the middle, so that thing in the middle might help where this one here might help when the sheet starts to sag between these two poles here. If you think about it, sticking up two tent poles, there's a little bit of a curve downward. You get a sort of curve downward here, but this pole might help pull it back up. Right, and so indeed that's exactly what you see here. Remember, we're looking at the imaginary axis, so we're going up the daisy and then all the way back down over here, right? And so if we're thinking about the imaginary axis, say from 0 to 10, we're looking at this portion here. So we should expect to see, if we look at h of j omega, we expect to see it's kind of flat and then maybe kind of trailing off, right? Because it's flat because of this this part here, and then it's kind of trailing off because the poles lose their influence on the rubber sheet as you get farther and farther away on the rubber sheet. So I hope that makes a little bit of sense, and I normally would be able to gesticulate wildly about this rubber sheet and the poles and the zeros, but really that's the best way to think about it visually, and that gives you a lot of insight actually into how you might want to design filters. Just thinking about what is the effect of, you want to stick a pole here so you can prop it up, and then you want to stick a zero here so you can pin it down. And those are that kind of intuition is really helpful when designing systems. So here's actually the frequency response produced by MATLAB, and we can see actually exactly the behavior we had. We have this flat portion here, and then it kind of decays downward. And so this thing allows low frequencies to go through, and if you notice it's with gain 1, right? And so because low frequencies are allowed to pass, we call this a low pass filter. And we'll talk a little bit more about that a little bit later. The phase behaves a little bit oddly. It kind of decreases and then jumps back up and then increases, but this discontinuity is not really a discontinuity. So if you look at this, this is at, say, it looks like it's about minus 180 radians, and this is, or degrees, and this is at 180 degrees. So these two things are actually, these are the same point, right? Because plus 180 is the same as minus 180. So this jump discontinuity in the phase response is actually just an artifact of how we're plotting things. Okay, so to try these things for yourself, you can use the butter function in MATLAB. It always makes me giggle. So butter is for Butterworth. And if you can provide it an order n, so this is the order, and this is the cutoff frequency. And this says give a CT filter. Right, so using these commands, this command, you can get the numerator and denominator that you can then stick into TF. So TF, if I don't know if you call it H butter, is equal to TF. Then you'll get the transfer function corresponding to the system object in MATLAB corresponding to this Butterworth filter. So you can try playing around with this this function to look at higher order Butterworth filters, which we'll take a look at a little bit soon, a little bit later. and look at the pole zero diagrams and the frequency response. And if you're interested in other types of filters, there's Chebyshev filters, elliptical filters, and Bessel filters, and maybe a couple others that I'm not mentioning here. But a lot of them, if you look at the documentation for those functions, they're going to require essentially a pole zero diagram for discrete systems, and that's going to come when you look at Z transforms, in order to design the analog system. So this is what we call the DT processing of CT signals, and the idea is that we would instead we'd have a sampler. So we take our signal x of t, put it as our sampler. We're going to get some kind of x of n, a discrete time signal, and then we're going to put it through h of n, and then we're going to do what's called interpolation, and then we're going to get our y of t. So this is y of n. This is the kind of picture that what happens, and this is this DT processing of CT signals, where you first convert the sampler convert using the sampler a CT signal to DT, do the filtering in DT, and then kind of reconstruct the original CT signal and spit it back out. And this is how like digital filters and DSP chips and stuff like that are doing the signal processing actually in discrete time instead of running an analog. If you're doing something like RF, on the other hand, the radio frequency stuff, then maybe you actually need to do analog filters because you can't build a sampler that's fast enough to do the filtering that you want to do. So this is a little bit of advanced topics, and we might come back to sampling at the end of the course, but certainly if you take the DSP course, you'll see a lot more of this kind of stuff.